pumping lemma. It is used to identify whether a language is regular or not. So, if L be a regular language, then there exists a constant n, then there exists a constant n such that for every string omega in L, such that the length of omega always greater than equals to n, and we break omega into 3 parts, or we can say into 3 strings, which are x, y, z, where omega is equals to x, y, z, such that y is not equals to epsilon, and the length of xy always less than equals to n. And the third thing, all k should be greater than equals to 0, and y to the power k z belongs to that language. And there are some rules. The first one rule is pick n, any value of n, but normally we assume n is equals to 7. Second rule is pick any string such that the length of that string always should be greater than equals to n. And the third one is find x, y, z such that y is not equals to epsilon. For all, the length of xy always less than equals to n. And the fourth one is find such k where x, y to the power k, z belongs to L, thus proves that L is regular language. Or we can say we find such k where x, y to the power k, z does not belongs to L, then this proves that L is not regular language. So first start with the language. Suppose we have 0, 0 plus 1 whole star. This is the regular expression for that language. What will be language? Language will be 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, and so on. This can be the language. So suppose, or what will the DFA? DFA will be start with the initial state Q0, move to q1 0 and make q1 as a final state and make a loop of 0 1 on q1. And suppose we choose n is equals to 7, as we set normally pick, or what are the rules, pick any n, and we assume suppose n is equals to 7, then because q0 to q1 there is a 0, so pumping lemma, pumping part, or we can say pumping lemma, start with a 0, so x cannot be epsilon. So x cannot be epsilon. Suppose we take a string omega is equals to 0 1 1 0 1 0 1. That is possible with this, because it can be any combination of 0 1 after 0. So suppose we assume x is equals to 0 here, and we suppose y is equals to 1 1 0 1 and z is equals to 0 1, because in the third one pick any omega such that is always greater than equals to n. So we take omega value as 7, because we pick n is equals to 7, so we take omega value as 7, 0 1 2 3 4 5 6 7. Okay, then we move to the next. What next? Pick n omega value such that greater than equals to n, and find x y z such that y is not equals to epsilon. So we find here x y z where y is not equals to epsilon, and the length of xy is always less than equals to n. Here we can see clearly that length of xy, what is the length? 1 2 3 4 5, which is less than equals to n. So, and what is next? Find such k that x y to the power y, x y to the power k, z belongs to L. So we cross check with this x y to the power k z. So what is this? 0 1 1 0 1 k 0 1, that where k is always greater than equals to 0. So suppose we take k is equals to 1, then if k is equals to 1, then that string belongs to L or not. So what will be the string? The string will remain same, like this, 0 1 1 0 1 0 1. So this belongs to that language. And if we take k is equals to 2, then omega belongs to that language or not? Let's check. Then what will the string? 0 1 1 0 1 1 1 0 1 y to the power k and 0 1, that is z x y to the power k 2 times, because k is equals to 2, and this is z. Obviously this is also belongs to L, because starting will be 0 and rest can be anything, because it is a 0 plus 1 whole star. It will be any combination of 0 1. So definitely this will also belongs to that language. So we can clearly see here, for any value of k, the language will always belongs to that language. The string will always belong to that language. So we can say clearly that the language is regular. With the help of that pumping lemma, we reach to the result that language is regular.